Hi, everybody. I'm Fabian. I'm a PhD student at the Department of Psychological Methods at the University of Amsterdam and a co-founder of Correlate Netherlands, which connects data scientists with organizations that advance the social good. And to me, climate change always felt like a distant, almost surreal threat. I learned about it in high school over 10 years ago, and I thought, it's pretty bad. But surely at some point, the politicians and the adults in the room would figure that one out and we could just move on. And, I tried as many to switch to a plant-based diet and limit air travel and no car and so on. But my involvement was limited to my individual consumption behavior. And so rattled on in the, the comfort and the privilege and the ignorance of my daily life. And what rattled me out of it was actually the onset of the COVID pandemic, where I realized that stability is not a given. So things can change quickly, dramatically for the worse. And so a year and a half ago in isolation with my girlfriend, I started to look into the climate crisis. So I read the scientific literature, I watched talks, I took courses, talked to climate scientists, invited them to speak. And I realized that it's much worse than I thought. And so when I came back to Amsterdam, out of my isolation, I prepared a workshop on the topic, gave it to my department. A couple of people attended. Somebody suggested I should give it again for broader audience. And so I did that for Correlate Netherlands. Unfortunately, we messed up the recording. So I'm recording this again 3 days later. So it's just you and me for the next hour and a half or so, talking about the greatest crisis our species has ever faced. And so here's what I have prepared. It's basically 3 sections in 5 parts. So the first part is to take a step back and look at the bigger picture. The second part is to look at climate impacts today and tomorrow, a small selection of the bigger issues. That will take about 30 minutes or so. And in the second section, I asked the question, well, why have we failed so far? And what can we do today? That's another half hour or so. And then the last part, so what I did originally in the workshop is to give like an hour interactive session with a nice tool called En-ROADS, an online climate simulator. I won't do that today, but I'll give you a broad overview in 15 minutes or so of the tool. You can play around with it yourself. So let's dive into the bigger picture. Mother Earth is an old lady. She was born about 4.5 billion years ago, and she's experienced a number of revolutions that made her what she is today. The first, undoubtedly, the inception of life, about 3.8 billion years ago, simple single cellular organisms. Another billion years ago later, one bacterium, the cyanobacterium, develops oxygenic photosynthesis and transforms in what's called the Great Oxidation Event, the atmosphere of the Earth, to hold energy-rich oxygen, which is what we use, all future life forms use as energy source. And so a couple of billion years later, multicellular organisms evolve. They colonize the land about 1 billion years ago, setting free phosphorus, which is an important nutrient. And about 540 million years ago in the Cambrian explosion, we have this wide variety of life getting started. That's a complexity revolution, if you want. But the climate was unforgiving. So life experienced 5 mass extinction events, killing at least 75% of all species. And 4 of these mass extinction events were due to wild swings in the carbon cycle. You got very cold, very hot. And the last mass extinction, about 660 million years ago, famously due to an asteroid killing the non-avian dinosaurs. But if we look at temperature reconstructions here, the last 60 million years ago, you realize it's quite wild. So you have here the Earth in a hothouse state. We have crocodiles in the Arctic. We have here the Paleocene, Eocene thermal maximum, clouds vanishing, sunlight reflecting clouds, very hot. And then, over the last 50 million years or so, a cooling trend set in. So here we get cooler and cooler and cooler. And here in the Mid-Pliocene Warm Period, about 3 million years ago, we are 3 degrees over the pre-industrial temperature, with sea level rises, sea level 17 meters higher than they're today. And 2.6 million years ago, we start the Quaternary period. We start getting into an ice age, where with oscillations here about a frequency of 40,000 years in and out of interglacial, so warmer period, and glacial periods, cooler periods. And about 1 million years ago, these oscillations changed into 100,000 year frequency. Not quite clear why yet. And these oscillations you see here, you have a cooler period, a glacial period, and you shoot up, you have a warmer interglacial period, you have a glacial period again, you have a warmer interglacial and a glacial, and so on and so forth, due to the Milankovitch cycle, so changes in the Earth's eccentricity and obliquity and the wobbliness. And about 250,000 years ago, Homo sapiens emerges, our species here, and is continuously on the road. So we have a nomadic lifestyle. And about 50,000 years ago, we exit Africa and colonize the Earth. And what we have, so here we in the 20,000 years ago, we sort of start to exit the glacial period, and we get into the current glacial period called the Holocene, about 12,000 years ago. And here, really everything we cherish develops. We settle down, we develop agriculture, we develop civilization, writing, the internet, but in the industrial period, we find and burn fossil fuels, which is organic matter, residues from the great mass extinctions. We burn them for energy, and that sets us onto this perilous path we are on now. So we have here a temperature rise, and these are now projections from Berkey et al. This is the worst case scenario, if you want, which is fortunately unlikely because we don't burn that much coal anymore. So that would put us back, into the hothouse Earth apocalypse, basically. On our current path, current policies set us up for 2.7 to 3 degrees of warming. So if this is the blue line here, that would put us back basically to the Mid-Pliocene Warm Period, where we have sea level 17 meters higher. What we want, of course, is to limit it to well below 2 degrees and ideally to 1.5 degrees, as agreed by all countries in the Paris Agreement, which would be this blue line, which would keep us into the Holocene variability of the climate. So keep us into in the state where we develop culture and agriculture and civilization. By the way, these slides I will make them available in the I will make them available to you. What I have interspersed here is basically links to the relevant literature, but also books that I find very good, and additional literature and podcasts and documentaries and talks and so on. Sometimes funny tweets, so that you could go through them in your own time if you want to know more. This is from the IPCC, the 6th assessment report. So there have been 6 assessment reports. They have different working groups. So this is from the working group 1, physical science, the working group 2 on adaptation and vulnerability, comes out next year, and the working group 3 on mitigation, which also is to be released next spring, I believe. This is from the summary of policymakers. So this is where all countries agreed to every single sentence and word. This is why you don't find any mentioning of fossil fuels, by the way. But what you see here is that indeed the warming is unprecedented in at least 2,000 years, and we are virtually responsible for all of it. So here you have these big Earth system climate models. You can run them without anthropogenic forcing, without the burning of fossil fuels and land use change. But then you're not matching the observed temperature. If you add human sources, you do match the observed temperature very well. So it's undeniable that the climate is changing and that we are the cause of it. If you're not convinced, I encourage you to follow this link and read more about it. So virtually, climate denial is really not an option anymore. There's a lot of delay, and we will talk about that later. So this basically, since the 1950s, if you see here, we've a rise, quite a steep rise in temperature. But there's more that happened in the 1950s. So the 1950s is what's called the Great Acceleration, where we really start to, populate, increase our population by a large amount, urban population especially. We grew our economy tremendously, and there was a lot of economic activity powered by fossil energy. We have a rise in fertilizer consumption. So we figure out through the Haber-Bosch process how to fix nitrogen, which is an important nutrient, from the atmosphere, and use it as fertilizers, which supports many billions alive today. We built large dams. We have an increase in water use, paper production, transport, telecommunication, international tourism. So we really explode, if you want, in the 1950s until today. And that has consequences for the Earth system. So if you look here, a couple of Earth system trends, where you have an increase in carbon dioxide from the burning of fossil fuels. You have an increase in nitrous oxide, also very strong greenhouse gas from mostly fertilizer, excess fertilizer. You have methane, also from agriculture, cattle burping rice paddies, but also in the production, transportation of natural gas, for example, or coal mining. And that gives rise to an increase in the temperature, global mean temperature of the Earth, which is what you see here. And very interestingly, here you have a plateauing. And there was debate back then whether we're actually entering a next ice age, whether there's global cooling or global warming. And that was due to aerosol pollution. So aerosols stay in the atmosphere a couple of weeks and reflect sunlight back. So they cool the Earth. And here, we had environmental regulations that made the air cleaner, and then it became pretty obvious that we were warming. Aerosols continue to cool the Earth today, actually. The latest IPCC report says about 0.5 degree of cooling. So if we were today stop all air pollution, the Earth will warm on average 0.5 degrees. Okay. We have ocean acidification. I think the ocean takes up about 25% of the carbon dioxide in the atmosphere, and that wrecks marine life. We have ozone depletion, and that problem we fixed in the Montreal Protocol end of the 80s, which has swapped the pollutant out. We have increase in marine capture, aquaculture, and so on. And we have nitrogen going to coastal zones and freshwater lakes and causing algal blooms and wrecking the life there. Whereas, of course, tropical forest loss and biodiversity loss, mostly due to agriculture. Again, we're eroding, for example, the rainforest. So we've really become, since the 1950s, a planetary scale geological force. And the Earth system scientists think about this, have a nice framework. It's called the planetary boundaries framework. So they have quantified 9 planetary boundaries, key Earth system processes that we would be good if we're not overshooting them. So some of them can't be quantified yet, like novel entities. So this is chemical pollution, for example, or the aerosol loading in the atmosphere. Others, we are below the boundaries. We're in a safe zone. This is ocean acidification and ozone depletion, which we fixed. Freshwater use, we're also not overshooting. But then there's some we are clearly overshooting. So here you have the biogeochemical flows. This is nitrogen and phosphorus, and the Earth system has natural nitrogen cycles and natural phosphorus cycles, and we're far overshooting them, mostly due to agriculture and artificial fertilizers. Land system change, we're also in the zone of uncertainty. And in biodiversity loss, this is in species extinction, we're also far overshooting the background rate. So there's a natural background rate of species going extinct, and species, getting created, if you will. And we are far overshooting this by a factor of up to 100, I think. And in terms of rates, then, in terms of the rate of extinctions, we are in a sixth mass extinction. In terms of the absolute levels of how many species are getting extinct, we are not, we're nowhere close to 75% of previous mass extinctions. But if we continue on our path, we will. So there's still time to avert a sixth human-induced mass extinction event. Climate change, we're also outside the safe zone. And so, yeah, so this is the bigger picture in terms of the Earth system. And there's a nice documentary with Johan Rockström and David Attenborough, just an hour talking about these boundaries, which I highly recommend. I met Rockström actually last summer. There was a workshop organized by the Potsdam Institute for Climate Impact Research on tipping points. And it was a 4-day event. And on the last day, we were all kind of exhausted and kind of a little depressed, but also energized, about the climate crisis and on. And then Rockström gave a talk. I think he just talked for 5 minutes or so, and about social tipping points and about we're at the precipice and all this agency we have. You can turn the ship around, and everybody was like, "Yeah, let's do this," and so on. He's a great communicator. I'll try to, at the end of the talk, give a little bit of that sense of agency and what we can do about it. But first, some of the impact and the bigger picture before we get there. So there's of course this is the donut economics framework from Kate Raworth using. I mean, this is really one of the great books of the 21st century, so I highly recommend it. Where she says, well, we shouldn't overshoot these planetary boundaries, but we also shouldn't fall short of key, social foundations, social thresholds, indicators. Water, food security, health, education, gender equality, housing, energy use, and so on. Unfortunately, no country is in this safe and just space for humanity. Okay, no country. So last week there was a new paper in Nature Sustainability by Fenning et al. And they looked at the development over the last 30 years of, I think, 150 countries. And they, plotted the number of biophysical boundaries they are transgressing. So some of the planetary boundaries you could downscale. Also added the material and ecological footprint. And they looked at the number of social thresholds these countries achieve. Okay. And what you find is that the rich countries are basically here in the top right, far overshooting biological and planetary boundaries, but achieving these social indicators. And most of the developed world, the global south, doesn't overshoot planetary boundaries, but also is not able to achieve these social thresholds. We need to be here in the top left, okay? So no country, in a sense, is sustainably developed. This is the bigger picture. This is the challenge for the 21st century. Okay. Second part. Climate impacts today and tomorrow. There are many climate impacts, of course. There's sea level rise, there are hurricanes, there's extreme flooding, there's air pollution, probably the most heinous and insidious one, killing 9 trillion people a year. I think there was an estimate in 2018, mostly to the burning of fossil fuels. So this is more than officially all the people from COVID died, and this is about half of the people who died in World War I, okay, which took 4 years, more people than in the Holocaust. So it's really, David Wallace-Wells has a nice piece on this recently. It's really, we need to reassess the brutality of the present, and this is happening today. But I want to focus on two of them, extreme heat on the one hand, and crop failures on the other hand. Now, this is from the IPCC, the 6th assessment report, Working Group 1. They had, for the first time, an interactive atlas. So you can play, it's quite nice. Here's a website linked to it. So you can play, see the world, you can play with historical temperatures, with projections under different scenarios. And the key point that I want to convey here is that the world doesn't warm uniformly. So on average, we've warmed about 1.1 degree over pre-industrial levels. but that is an average across the whole world. The land actually warms about twice as fast than the ocean. So we've warmed an average already nearly 2 degrees on land. And across land surface, it's also different. So for example, the Arctic warms much faster, 2 to 3 times than other parts of the Earth, with devastating consequences, as we'll note later. The tropics do not warm as quickly, but the tropics are already pretty hot, okay? So any additional degree there has a much greater effect on the conditions for life than, for example, in Europe. And we'll see this in a moment. Now, how do we, so, I mean, for example, the Netherlands here already warmed 2.1 degrees in 2020, is up to, heads another 4 degrees. You have China also already nearly 2 degrees. And then you have Brazil, less than 2 degrees closer to the tropics. And you can look at the country you reside in that website. And there's no doubt that climate change already has increased regional heat waves in intensity and frequency and duration. Indeed, a third of heat-related mortality is already attributable to climate change. It's already a big problem today, but it is projected to get worse. So let's look at how we reason about the future. We cannot really predict how society develops, right? It's a hard problem. So what people in the climate community do, and the policymakers, they look at scenarios of how society develops, the so-called shared socioeconomic pathways. And there are 5 of those. You have, and they are distinguished in terms of the mitigation challenges, so how hard it is going to be to avoid dangerous climate change, and the adaptation challenges, so how difficult it will be to adapt to a changing climate. And ideally, you have SSP1, which is sustainability, where you switch from economic growth to well-being, and you slowly but very surely achieve your climate targets and so on. You have a middle of the road, which is continuing on sort of historic trends. You have regional rivalry, where the sort of international communication breaks down, and it's going to be, it will be hard to agree on anything. Sort of very high mitigation, very high adaptation challenges. There's inequality, with increased inequality within countries and across countries, and you have a rapid growth scenario fueled by fossil fuels, just growing economy a lot, and you have technological developments. So these are scenarios for how society develops, and then you compare them with basically a mitigation scenario limiting warming to a particular degree, and this is then given in watts per square meters at the end of the century. So that's basically the radiative forcing, how much energy comes, the energy flux, how much energy comes in a square meter and how much goes out. And 2.6, for example, 2.6 watts per square meter is relatively low, and 6 is much higher. So that gives you that quantifies the radiative forcing, which is leads to the warming. So for example, here you have the baseline scenario for rapid growth it would be absolutely catastrophic if you continue to burn fossil fuels a lot. You reach up to 6 degrees of warming, but you can combine that with certain mitigation scenarios where you, in this scenario at least, have a lot of carbon capture and storage, for example, and then you achieve a lower temperature. And sustainability, you don't even reach these high levels. You do it more sustainably, and you limit warming to a lower degree. But let's focus on the SSP2, which is kind of just a continuation of historical trends. And let's look at SSP2 4.5 watts per square meters, which would lead to about 2.7 degrees by the end of the century. And this is about, this is in the range of what current policies would lead us to. So let's look at extreme heat. And this is from Quiggin et al. This is a report by Chatham House, came out I think in September, based on a paper by Arne et al. In 2019. So even though it's a relatively recent report, the underlying science is a little older. And what you see here is the number of people impacted by major heat waves each year. So even 2020, you have about 1.5 billion. So this is millions of people, and that would just increase quite dramatically actually as we go on. 2040, you have about 4 billion. This is the median estimate, and the uncertainty comes from So this is you have an ensemble of climate models, and they also have prior distributions over, say, the equilibrium climate sensitivity, or just uncertainties in the carbon cycle. It could be much better. It could also be much worse. Regionally, you have, this is the, I should say that a major heat wave is a heat wave where you have temperatures in the 99 percentiles. It's extremely hot for that particular region for at least 4 days. What you have here, the regional impacts in 2040, looks like this. So you have it basically everywhere, an increase in heat waves, especially in the tropics, that get hammered. And by 2050, you have more than 70% of people in every region that will experience these major heat waves. And urban areas, of course, cities, urban island effect, cities warm up to a larger extent. This ignores a combined measure of, or this ignores the factor of humidity. So if there's a combined measure of humidity and heat, it's called the wet bulb temperature. And if you're too hot, you sweat to cool down. Now at a certain level of humidity and temperature, you can't do that effectively anymore. And that measures 35 degrees wet bulb temperature. So this is 35 degrees at 100% humidity. If the humidity is lower, you would have to have a higher temperature. But at 35 degrees, you can't sweat effectively anymore. You just cook to death within hours. At 32 wet bulb temperature, there are severe restrictions on physical labor outside. You have to have a lot of pauses and cool down. You can't do that effectively. And a recent paper last year showed that, look, while climate models project the first 35 wet bulb temperatures by mid-21st century, actually, if you look at the data, you see that some subtropical locations have already reported wet bulb temperatures in that extreme. And they say our findings underscore the serious challenge posed by humid heat that is more intense than previously reported and increasingly severe. And just this summer, Zangeral showed that for every 1 degree temperature rise in the tropics, there's a corresponding rise, 1 degree, maps to 1 degree, in the wet bulb temperature, in the extreme wet bulb temperatures in the tropics. So there's a nice proportionality here. Of course, it's devastating for the region. And so these heat waves basically ignore this. Now, just a couple of weeks ago, the Met Office, the UK Met Office, released a press release in a report saying that 1 billion face a heat stress risk. So this is wet bulb temperatures of 32 degrees from a 2-degree rise. Today, it's about 70 million, and that would rise to 1 billion for a 2-degree temperature rise. And the median for a 2-degree temperature rise is in 2050, based on our current trajectory. And you see here, this is the map where you have these extreme wet bulb temperatures larger than 32 degrees for more than 10 days per year. This is at 4 degrees warning. I emailed them, but they don't have the map for 2 degrees. But you see that this is mostly in the tropics. So there's really an injustice element here, and I'll talk about that later. But you don't need to read the scientific literature and dig into that to realize that, okay, maybe things are actually worse than we've assumed. So just last summer, we had this heat dome in Canada and the Western US that, the jet stream got kind of blocked and the weather patterns couldn't move for days and just become increasingly hot. So you have temperature records shattered by up to 9 degrees, okay? And here's Michael Mann, one of the world's leading climate scientists, saying there's something else going on with this heat wave. And indeed, with many of the very persistent weather pattern extremes we've seen in recent years in the US and Europe and Asia, where the models aren't quite capturing the impact of climate change. And here's Jon Röckström also saying, look, these weather anomalies were not represented in global computer models that are used to project how the world might change with more emissions. And the climate science community was a very good track record of forecasting the extent of warming that we have. In fact, even as we'll later learn, ExxonMobil predicted very well the extent of warming today in the 80s. but it's just that the climate impacts have been underestimated. There's an interesting article, an interesting discussion. If you're into the sociology of science, where these authors argue, Naomi Oreskes and Michael Oppen and others, that the climate science community has had historically a tendency to err on the side of least drama, if you will, mostly because there are norms. I mean, if you're a scientist, you know this. There are norms within science to restrict. You have to be very certain to say something, and you really don't want to have a false positive. If you want false negatives, you don't weigh so much. But there's a tendency to first figure out a lot and then cautiously say, look, this is problematic. This has gotten a little bit better. I talked to Michael Oppenheim on Twitter a little bit. This has gotten better in recent years. But it's interesting that there's something within science that makes it inherently conservative. Okay, so we looked at extreme heat. Let's look at agriculture and crop failures. Now, this is from the IPCC special report on climate change and land, where we have about 130 million square kilometers of ice-free land surface, and 1% of that we use for infrastructure, for cities and so on. 12% we use for growing crops. 37% we use for cattle, beef and so on. 22% we use for forests and to get wood to build houses and chairs. And then about 30% is either ecosystems we don't touch, or it's just just rock. We can't do anything with it. But what you find is that about 50% we use for agriculture. It's an enormous amount. And basically, around the world, this is the share of land used for agriculture. But there are major breadbaskets. Certain regions, for example, China exports most of the rice. You have the United States exporting most of the maize and soybeans, and you have Europe exporting most of the wheat. So there are certain core breadbaskets area for particular major crops. And you might have heard that climate change might make agriculture impact on agriculture due to droughts or due to just hot spells and so on. And so I was curious to look into the search. Just Googled agricultural drought, climate change, in 2021. And here's what I found. Okay, so here you have severe drought devastates Washington State's wheat crop. You have drought withers Western Canada's spring wheat, worst year I've ever witnessed. You have Mexico, water supply buckles on worsening drought, crops at risk. You have record-breaking drought in Chile, offering bountiful proof of climate change. You have Brazil, besieged by COVID, now faces a severe drought. You have record droughts in Latin America, in Paraguay, in Brazil, Argentina, Mexico. You have it in the Middle East. You have Jordan facing one of the most severe droughts in its history. You have Iran buying record volume of wheat after the worst drought in 50 years. You have here from The Guardian, the challenge for us now is drought, not war. Livelihoods of millions of Afghans at risk. You have at least 1 million people facing starvation as Madagascar's drought worsens. You have a drought in Kenya, putting 2.1 million Kenyans at risk of starvation. You have Angola, millions facing hunger as thousands flee their homes as drought ravages the south of Angola. So it's really already here. You might not see it because maybe you only read The Guardian or the New York Times and you see, single reports. But if you really just start to look into it, you realize, okay, it's here. And this is projected to get worse. So this is again the same report. What I'm showing here is the proportion of cropland exposed to severe drought of 3 months or more. And here in the 2020s, you have about 20% of the cropland. You increase and it just gets worse. 2040, about 30%, 2050, you have 40%. And this is again the median, right? Depending on how lucky you are with the uncertainty, it could get much better, it could get much worse. And you have that basically everywhere, right? So you have farmers in the worst affected areas are likely to experience severe agricultural drought impacting 40% or more of their cropland every year in the 2050s, at a time where we need to estimate, say, we need to produce about 50% more food because we have a larger population that also wants to consume more. So during the 2040s, there's a 50% chance of synchronous crop failure. So we have multiple bread baskets having at least, I think, a 10% reduction in their agricultural output. And this is, I just looked at severe drought, but there are also just damaging hot spells that are increasing, or just in general, the growth period getting reduced as the climate crisis worsens. So this was extreme heat and crop failures. And of course, that leads to, I mean, as you said, if there's famine, if you don't have anything to eat anymore where you are, that leads to people moving. If it's too hot for you to literally live where you are, people will move and have a right to move. So there's some estimates by the World Bank, 2050, about 220 million people could be internally displaced. If we get our act together, we can reduce it to 70 million. Some estimates are in the orders of a billion people moving. It's difficult to assess this because people, of course, don't want to move. I mean, you don't want to leave your home unless you're really forced to. So depending on what we do also in terms of adaptation in these regions, providing them with, the infrastructure to shelter, to avoid these extreme heat waves, such as, fixing the climate problem as best as possible, we can reduce that. But certainly, I just look at the refugee crisis that, that we had in Europe. I mean, we got about 7 million people or so, I think the estimates say. I mean, increases by an order of magnitude more, and you realize how toxic the debate could be in the global north and in Europe, and how it could slide into this eco-fascism and climate barbarism, as Naomi Klein calls it. So this is a real risk. But another thing I want to talk about is uncertainty. And it is generally not on our side. And I've listened to many climate scientists speak, and then I ask a question where I think we should know this, okay? And then oftentimes they just say, yeah, actually we don't know, right? Or I just wrote a grant proposal on this. Yeah, and that's, of course, I mean, it's fine in a sense. I mean, they're doing God's work with all the climate science they're pushing forward, but it makes you realize that we are conducting this vast geophysical experiment, knowing in some sense relatively little about the complex Earth system. So if you just look at, this is a map of tipping points, which or tipping elements, which the physiology of the Earth system, if you want. So Tim Lenton and others drew this map in 2008, I think, 2008 in a PNAS paper, where they isolated the expert elicitation, and they isolated regions that can have multiple stable states. So a state that is good for us, and a state that is bad for us, if you will. So look at the Greenland ice sheet here. So that has a temperature threshold. I think the best estimate is 1.6 degrees, and with a range of 0.8 to 3.2. And if that threshold is reached, there are self-amplifying feedbacks that lead to runaway melt. So you cross that threshold, you can't go back, in a sense, unless you really, cool the Earth down again. And that would lead to, at least, 2 to 7 meters of sea level rise this is on a century timescale. It could take a millennium to all disintegrate. But other things can have effects on a human timescale, if you want. So the Amazon rainforest generates most of its heat at a particular temperature threshold, combined with deforestation, that makes it worse as well. It can't do that effectively anymore, and then it dries out by itself. So at some point there may be a tipping point where it just tips into a savanna, and that would release billions of tons of CO2 into the atmosphere, worsening the crisis and, of course, wrecking the local ecosystem and the people there. You have the Atlantic Meridian overturning circulation, where part of it is the Gulf Stream that brings heat from the tropics to the northern hemisphere. That has slowed down, and that also has a tipping point where it then can stop. stop to bring the warm temperatures to the north and the cold to the south. And that can have devastating effects for Europe in terms of a cooling period on agriculture. And then there are things like the permafrost, where you might not have an alternative stable state where it all gets released, but you have non-linear events like thawing and wildfire that can lead to an abrupt increase in emissions of CO2 and methane. And if you read the latest IPCC report, they say, yeah, we have a high confidence that there's going to be increased permafrost loss, but with a low confidence in the size and the timing of the emissions, right? So that's exactly what you don't want. And these things have happened in the past. So there's a nice review article in Nature Geoscience last summer, where they looked at past abrupt changes. And they said that, look, the geological record shows that these abrupt changes in the Earth system can occur on timescales short enough to challenge the capacity of human societies to adapt to these environmental pressures. And at the forefront of the science, if you want, is the notion that these tipping points can influence, tipping elements can influence each other and cascade. So you have, for example, a reduction in Arctic sea ice. You have less albedo, so you're more warm in that area. That, of course, influences the permafrost thawing. It also influences the Greenland ice sheet, increasing the melt. That could slow down the AMOC, and that could lead to less cold being transported to the Amazon, leads to more heat there and to more droughts and to potential tipping. If you look at the IPCC assessment of these tipping elements, this is from Lenton et al. 2019, you see that in 2001, we were like, yeah, I mean, maybe at 5 or 6 degrees, there's a high level of risk that we trigger some of these tipping points. And that got downgraded in a sense as we moved on with the science. So in 2009 here, maybe at, I don't know, maybe at 3 or 4 degrees, you have moderate to high risk. 2014, you start to get at 2 or 3 degrees. And here, 2018, also already at 2 degrees, you might trigger these tipping points. So uncertainty is not our friend. This is a nice image that I like, Stefan 2018, where they look at a stability landscape, very simplified, of course, but it makes the point that, we've historically, again, in the past 2.6 million years in the Ice Age, the Quaternary period, we had this glacial interglacial dance, this limit cycle, cooler period, and then going up again in the glacial, going down again in the cooler period. But now we are at the precipice, in a sense. We can steward the Earth system back into this stabilized state, or we can continue to fail, to emit and to degrade the biosphere, and reach these tipping points that can amplify warming even further. So we might not be able to safely land at 2 degrees, but we might cause tipping points that may cascade and push us further into the climate crisis, into kind of a hothouse Earth. And there's a nice book, I mean, to get your imagination going, there's a nice book by Naomi Oreskes, which I greatly admire, and Eric Conway, 60-page book on the collapse of Western civilization. So I encourage you to check this out. There's also a book by Kim Stanley Robinson, The Ministry for the Future, that gives you some perspectives or tools to reason about the future, which is very difficult. Here's John Schellnhuber, the founding director of the Potsdam Institute for Climate Impact Research, and he says, I think, in a recent interview, he says, I think we have more than a 5% chance of succeeding, but it's definitely less than 50% in my view, okay? And he says, but what is the option, yeah? If we have a final chance to save our culture and our civilization, I'm just compelled to do it. And there's a scene in The Lord of the Rings I think about a lot in this context. And it is Frodo who says, I wish the ring had never come to me. I wish none of this had happened. And then Gandalf says, so do all who live to see such times, but that is not for them to decide. All we have to decide is what to do with the time that is given to us. So I have a short pause here. Maybe you can stretch your legs and notice how you sit. Get another coffee or tea or some water. Before I move into the second section, if you want. And here we ask the question, why have we failed so far? And the fact that we failed is pretty obvious. So here we look at the carbon dioxide emissions in gigatons per CO2. This is only from fossil fuels. So there's no land use change or other greenhouse gases, just from fossil energy. And here in the first IPCC report, 1990, there. Since then, last 3 decades, we have added 50% of all historical CO2 emissions. Okay, so 50% of the problem we have created since we knew absolutely that there is a problem. And this is here split into developed countries and developing countries, where over 80% of the population lives. And I'll talk about this split later. So we have failed. Yeah, in my lifetime, we've created 50% of the problem. This is just from fossil energy, and as a kind of a background knowledge, here the main greenhouse gases that are responsible for global warming. You have 60%, more than 60% coming from CO2 from the burning of fossil fuels, energy related. You have CO2 from deforestation. I mean, if you burn wood, forest biomass contains mostly carbon that gets into the atmosphere. You have CO2 from cement and industrial processes. You have CH4, which is methane from agriculture, from cows burping from rice paddies, and also from industry when you mine coal or when you produce and transport methane gas or natural gas. And you have N2O or nitrous oxide from agriculture. And you have certain F gases used as refrigerants in industry. This is from the IPCC assessment report, the 5th assessment report, the working group 3. If you look at the leaked IPCC working group 3 report that comes out next year, the picture barely has changed. And CO2 stays in the atmosphere for hundreds, even thousands of years, while methane stays there for about 12 years, but has a much stronger warming potential. So on a 20-year timescale, there's about 80 times the warming of CO2. And nitrous oxide has about 300 times the warming of CO2 on a 100-year timescale, and stays in the atmosphere about 116 years. So these are powerful greenhouse gases in addition to CO2. But there is a very nice relation. This is from the IPCC report, the latest one. There's a nice relation between the cumulative CO2 emissions and the global mean surface temperature increase. So there's a near linear relationship between these two, and you see here the historical warming, and you can fit a line in there pretty nicely. And these are projections we've mentioned earlier. But that nice relationship gives you allows you to ask the question, well, okay, I mean, I want to limit warming to 1.5 degrees. How much CO2 can I still burn here? And if I want to limit it to 2 degrees, how much CO2 can I burn then? And that gives you what's called a carbon budget. So here you see, it's a little busy, but this is the table also from the IPCC summary for policymakers. You see, okay, we've warmed about 1.1 degrees. We've burned about, or we've emitted about 2,400 gigatons of CO2. Gigaton is a billion ton. And then you can ask, well, I want to limit it to 1.5. This adds 0.4. And then you can say, well, what is the remaining carbon budget from the beginning of 2020? And there are uncertainties associated within the carbon cycle. For example, it gives you, probability distribution. Then you can say, well, I want to be pretty sure I don't break this. And then you have about 300 gigatons of carbon emissions left. So we emit, about 40. and that would give us, you know, less than 8 years on our current emission trajectory before we breach this carbon budget. You can have a higher carbon budget if you increase the warming limit, of course. And then you have, I mean, that also depends on the things you're doing with, you know, other greenhouse gases like methane and nitrous oxide and the F gases. And depending on your reductions there, you can increase your carbon budget by here 220 gigatons, or decrease it by that factor. So these other greenhouse gases matter a great deal as well. In fact, even if we fix our carbon emissions, if we don't fix agriculture, we blow our carbon budgets for 1.5 and 2 degrees. So it's a complicated problem, but you can look at this in a graph as well. So here, this is from a Carbon Brief article. So Carbon Brief is really a tremendous resource for climate science. I mean, do check it out. But here, what they plot is the historical CO2 emissions. So this is from CO2, this CO2 from land use changes and from fossil energy. Here, this is the COVID dip, a reduction about 7%. And this is what we would need to do to limit warming to 1.5 degrees without the use of large-scale negative emissions technology, so without sucking it out of the atmosphere later in the century. And I'll talk about this. And here you see it's pretty steep. I mean, this is pretty steep. So it's about a 7 to 10% reduction every year. And Rockström has a nice paper in Science with others about the carbon law. Basically, a good rule of thumb is you have to half it, every decade. So you half it 2030, you half it 2040, you half it 2050, and then you suck out the remaining bits. But I mean, that is a transformation that is unknown in human history. The longer you wait, the more brutal it becomes, of course, because it's a cumulative problem. So if you don't do anything now, you wait a year, you've added another 43 tons. That doesn't go away, that stays there. It adds to the problem. If we have gotten our act together in 2000, it wouldn't have been a walk in the park, but it would have been easier, right? If we started in the 1990s, probably would have been a walk in the park. So we have failed so far. Now, why have we failed? And there's a great review article just came out last October on that question that asks, 3 decades of climate mitigation, why have we failed to bend the emissions curve? It's an interdisciplinary team, and they looked at it through 9 thematic lenses. And the key outcome kind of was that we have failed because of power. Yeah, so they categorize this power into 3 clusters. The Davos cluster has the power to set the narrative and the way we view the climate crisis and the associated problems. We have the enabler cluster that consciously or unconsciously supported a kind of a status quo, business as usual approach to dealing with the climate crisis. And then you have the ostrich cluster, where ostrich is the bird that puts a hand into the sand, doesn't listen, blah 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 blah, doesn't want to engage. And I'll take it as an inspiration to talk about one aspect for each of these clusters. So I want to start with the vested interests of the fossil fuel industry, and it might be good to historically look at society's understanding and its actions on the climate, and big oil's understanding of the problem. And this is just a really short summary. Ben Franta has given a great talk on this two weeks ago, so I encourage you to check it out. But if we look at society, I mean, we have known about the greenhouse effect for over 200 years. We knew that if you add carbon dioxide, it leads to warming. But what wasn't clear was whether the burning of fossil fuels could add to the atmospheric concentration of CO2. And Keeling showed this in 1960, the famous Keeling curve, that indeed we're adding CO2 to the atmosphere. There was an environmental report commissioned by the president of London, B. Johnson, who said that yes, fossil fuels are the problem, climate crisis, or that there is going to be a problem with the climate, with the warming. As I said earlier, there was this debate, in the 60s and 70s of whether we're cooling or warming. In the 70s, it became pretty clear, okay, we're on a warming trend. So we stopped the air pollution in that part of the world that led to to getting away with this cooling trend, this masking of the warming, and then it was clear that we're warming. James Hansen famously testifies before Congress in 1998. We have the same year forming of the IPCC, the Intergovernmental Panel on Climate Change. And 4 years later, we have the UNFCCC, that's sort of the international treaty where, of countries dealing with dangerous climate change. We have, then with conference after conference of the parties. We have the Kyoto Protocol, we have the Paris Agreement. We recently had the Glasgow COP. At the same time, this is now Big Oil's understanding. In '59, it was warned by the famous physicist Edward Teller, saying, look, your product is a problem. That's going to lead to a changing climate. In 1965, just 3 days after this report, the president of the American Petroleum Institute, which is the trade association of the oil majors in the United States, warns Big Oil, saying, look, your product is a problem. We have an issue here. They commission scientists looking at it independently from this report, finding the same thing. You have Exxon. You have an internal research program by Exxon. They look into the problem as well. They make these now famous projections, of the warming that we would see in the 21st century, and are pretty much spot on. They also create reports about the potential catastrophes that would unfold if we do business as usual. But they abandoned this research program because it became clear, actually, this could harm our bottom line. So they ignored the problem. 1980, again, the API argues for a tripling of coal, even though, again, 20 years already, they knew of the problem, that they were the problem. This is the first, as Ben Fent has uncovered, the first basically known public disinformation campaign. You have in '87, a strategy meeting of the oil majors where they say we need to emphasize uncertainties. We need to stress the cost of action. We need to focus on policies that do not threaten fossil fuels. Look at agriculture and deforestation and so on. Put the blame somewhere else. And we need to insist on detection before action. And we need to violate the precautionary principle. And they did then implement these strategies. So they had the Global Climate Coalition, which is, a lobbying group that, they funded think tanks and economists and politicians to delay, to deny, to spread disinformation, uncertainty, and doubt. So there's a really fantastic book by Naomi Oreskes and Eric Conway called The Merchants of Doubt, looking into that history. And now basically we don't really have hardcore climate denial anymore of the oil industry, as Michael Mann explains nicely in his recent book, The New Climate War. It's more a delay, the delaying strategies. It's not going to be that bad, or maybe we can be part of the solution. Natural gas could be a clean bridge fuel and blah blah blah. So they have delayed action on climate for 4 decades, at least 4 decades, and there is no doubt that this has cost us a lot. Okay, and I am sure that they will burn in hell for it. The question that's really up to us is whether they burn in hell on earth or in the Christian hell. So this was basically the vested interest of the fossil fuel industry, and in some sense, it's the more obvious villain, right? I mean, there's this great documentary called The Corporation in early 2000s, so illustrating, corporations have wrecked the societies, or ignored environmental regulations and workers' rights and so on for a long time in pursuit of profit. It's just that now with the oil industry, it's just that the problem is so big. I mean, forget about big tobacco, which was terrible, but that could put into the question the continuation of our species, right? So it's just that the scale is so enormous, and the incredible knowledge, detailed knowledge that they had early on is what is shocking here. Okay, yeah. Vested interest of the fossil fuel industry. Set the status quo, the narrative delayed, and so on. And then there's a more subtle, if you want, point that the authors make and that I want to elaborate on, is about mitigation modeling. So how have we, as a scientific community, how have we tried to understand climate action? And at the core, again, are these scenarios, these narratives about the future. And these get fed into huge, complex, integrated assessment models that combine, knowledge about the economy, energy system, land system, and climate, and these interactions. So it's really, if you want, a crown crown achievement in terms of modeling the complex system, the coupled complex system of the climate and the economy and the human system. And you add then, you add your scenarios and you make many assumptions, and then you can ask, what happens if I stop burning coal, right? How does the system react, and what do I get out of in terms of emissions and economic outcomes and climate goals? But you can also ask, well, I want to limit warming to well below 2 degrees. How do I have to optimize all these? How does the model optimize to limit warming to 1.5 degrees? So what does it do? And these models, while very complicated and nice and so on, have been criticized a lot, strongly because of they're based in this new classical economic framework. So where you have rational agents, they have full information, they optimize their utility. You have the starting assumptions that markets work, that there's no wasted investment, there's no unemployment. And so per definition, any reduction in economic activity, because market is optimized, by definition a cost. And you have the strong assumption that economic growth can be decoupled from emissions, as is called green growth. So you don't really have to change the status quo, basically, the economic system, because you built these assumptions into it, even though just empirically there's no evidence of the decoupling happening fast enough to limit warming to climate targets. But you also have something like the discount rate, where you weigh near-time costs more heavily than those in the future. So this is basically the time value of money. You'd rather have 100 euros today rather than maybe 150 in 5 years, because you can invest with that money, you can do something with that money and so on. But whether that translates to saying, well, action today is more costly than action tomorrow, I could delay a little bit more, put this on future generations, that's a big jump. They underpredicted the fall in the cost of renewables, and predicting technological change and innovation is very difficult. But by having failed on that, they overstated the cost of rapid decarbonization and relied a lot on continuation of coal with carbon capture and so on. They focused generally on market-based solutions, because again, if the market is optimal and it works, then of course I want the market-based solutions, so on carbon pricing. And they focused a lot on technological innovations such as large-scale negative emissions technologies. And that was quite shocking when I learned about this first. So here, this is from a paper by Anderson and Peters in Science. This is a standard scenario. If you want, you have the historical emissions, they rose, and then you have a kind of a future scenario where you have here in orange the emissions from fossil fuel industry, and land use change, and that goes on quite a bit actually at the end of the century. But at some point, you realize in the 2030s, and that gets ramped up increasingly. At some point, you realize negative emissions, so you suck carbon out of the atmosphere at a pretty large scale. I mean, this is 10 gigatons per year, okay? And that offsets the lack of reduction here. So you offset basically this overshoot with these with this negative emissions, so you reach a net emissions, and then if you reach net zero, you stabilize the climate. So there's a kind of an inherent delay strategy where you say, look, the action today is costly, more costly than tomorrow because of the discount rate, and I'd rather have some technological innovation in the future rather than having a rapid reduction in emissions today. And the problem is that exists on paper. So these negative emissions, they don't exist at the large scale that is required here. So recently, the direct air capture a facility, I think, opened in Iceland or so, and that sucks out about 3 seconds of emissions in a whole year. So it's nowhere near at that scale required. So we need to do a lot of more funding in that. But the fact that this is assumed in the majority of models is quite heinous. And they rely here not on direct air capture for the most part, but on bioenergy carbon capture and storage. This is BECCS, where you grow biomass and trees. Then that by virtue of that you suck out the carbon from the atmosphere, and then you burn that for energy, and then you capture the carbon that would come out from the burning, and then you put it in the ground and you store it away. This is carbon capture and storage. The issue here is that the land, this is from an Oxfam report last summer, the land required to grow these crops for energy is larger than the cropland worldwide, and that that would have devastating consequences for biodiversity, planetary boundary we're already overshooting, and also have effect on food security. So there are interconnections in the complex system that with the negative emissions technology are not taken into account. Okay, negative emissions. There's this other issue of whether you can decouple the emissions from economic growth. And there are reviews recently last year by Helmut Haberl and others saying that this is not happening at a scale fast enough, and we probably shouldn't rely on it. So there are recent calls for climate mitigation scenarios that don't rely on economic growth. Certainly not economic growth in the global north, because we don't need more material consumption. The global south is a completely different question. They need to develop a lot of infrastructure and so on and so forth. But in the global north, definitely not. We don't need it for well-being, but it is assumed, again, because economic growth is per definition good in the new classical economic framework. Now, okay, and there are some resources here that you can check out on your own. I don't want to spend too much time here. What I do want to mention are simple assessment models, integrated assessment models. So we have these complex assessment models at the core of the IPCC reports of the mitigation scenarios and policy making, but they're also more simpler downscale versions of that are very simplified economic model, very simplified economic climate model. And these are used for assessing what is called the social cost of carbon. You've certainly realized that fossil fuels are way too cheap, given that they cause climate change and air pollution and so on and so forth. So we need a way to price them, to put a carbon price on them. But the question is, well, how high should that carbon price be? And these simple integrated assessment models, they use temperature projections and then some function linking that with economic damage, which is quite arbitrary. They link that, and then you can say, oh, okay, this will lead to that much cost, and so I calculate back how much I should price carbon. And they've been used by Obama, who by Trump and so on and so forth. So this is a kind of a key thing, the social cost of carbon. Now here's Robert Pindyck in 2013 writing about these models, and he asks, what do the models tell us for climate change policy? And he says, very little. A plethora of integrated assessment models have been constructed and used to estimate the social cost of carbon and evaluate abatement policies. These models have crucial flaws that make them close to useless as tools for policy analysis. Certain inputs, the discount rate, are arbitrary, but have huge effects on the social cost of carbon estimates the models produce. The model's description of the impact of climate change are completely ad hoc, with no theoretical or empirical foundation. And the models can tell us nothing about the most important driver of social cost of carbon, the possibility of catastrophic climate outcome. And he says, integrated assessment model-based analysis of climate policy create a perception of knowledge and position, but that perception is illusory and misleading. I mean, the whole paper is great, but I think already the abstract tells you a lot. This was 2013. This is Steve Keen in 2020, writing, forecasts by economists of the economic damage from climate change have been notably sanguine compared to warnings by scientists about damage to the biosphere. This is because economists made their own predictions of damages using three spurious methods. Assuming that about 90% of GDP will be unaffected by climate change because it happens indoors, using the relationship between temperature and GDP today as a proxy for the impact of global warming over time, and using surveys that diluted extreme warnings from scientists with optimistic expectations from economists. Nordhaus, he is a climate economist, got the Nobel Prize in 2018, has misrepresented the scientific literature to justify the using of a smooth function to describe the damage to GDP from climate change. So this is this damage function. Correcting for these errors makes it feasible that the economic damages from climate change are at least an order of magnitude worse than forecast by economists. And they may be so great as to threaten the survival of human civilization. So these guys don't mince words. Yeah. But if you just read these two papers and you're in science, you think yourself, I mean, that's pretty brutal. It's pretty brutal stuff given the issue that's at stake. So this is mitigation modeling, and the point here basically is to say that it is not value neutral. Just because you create a model, you have a computer code, you write it in the language of mathematics, it doesn't mean it's objective. It is not value neutral. You add your values in how assumptions about how the economy works, and assumptions about the discount rate, and so on and so forth. It is not value neutral. And it has these authors, and I would agree, delayed a kind of a rapid action, treating the climate crisis as the emergency that it is, but rather to have these business as usual kind of approach. But maybe the most pernicious thing is here in the ostrich cluster. And I want to talk about inequity in high carbon lifestyles. And really at the core of the climate crisis is a great injustice. So here, this is from the United, the emissions gap report in 2020. So here you have the average per capita carbon emissions in 2015 in tons of CO2 per capita. And here on the x-axis, you have the population split in percentiles based on income. So here you have the top 1% income earners, the top 10%, the middle 40%, and the bottom 50%. And this is the horizontal line showing in 2030 what the average per capita consumption should be to limit warming to 1.5 degrees. And you can calculate this because you have this near linear relationship between emissions and temperatures. You can get a carbon budget, and then you split that fairly across all people living on the Earth. And what you see here is the top 1% are vastly overshooting what is consistent with limiting warming to 1.5 degrees, by a factor of 30 or so, more than 30. You have the top 10% also vastly overshooting by a factor of 10 or so. You have the middle 40% overshooting maybe 2, 2.5, 3 times. And then the bottom 50% can actually increase their carbon emissions, by at least a factor of 2. And if you look at this pie chart here, you have the top 1% in population, okay, a small section of the world uses 15% of the emissions. So this is in 2015. I don't think it's gotten better. The top 10% in total emissions of 50%. And, the bottom 50%, just 7% of emissions, okay? So, there's an almost unbelievable amount of inequality here. And you don't have to be brutal to be in the top 1%. These are averages, and might do much better, might also do much worse. The top 1% is 94,000 euros a year. Top 10% is 33,000 euros a year. Of course, there are certain individuals, billionaires, that generally have a much higher carbon footprint. This is 30,000 tons of CO2 per year. Mostly, because of these yachts or just private jets and helicopters or huge second houses and so on and so forth. But this, and the top 1%, this is where power resides. They benefit from this inequality. They benefit from the status quo. And that inherently leads to delay on climate action, because they don't feel the climate impacts yet, as we've seen previously. It's mostly so far felt by the global south. So there's a disconnect. And And scientists in the past couple of years have started to to argue, look, we should shift the focus from the super poor to the super rich. Because of this inequality. Scientists, there's a great review article, have warned on affluence for the climate. And here's a great paper by Christian Nielsen and others in Nature Energy just in September, when they talk about the role of high socioeconomic status people in locking in, but also having the potential to rapidly reduce greenhouse gas emissions. And this picture I showed you earlier kind of summarizes it, right? So you have rich countries, global north countries that exploited the global south, colonialism and so on and so forth, and now it's climate colonialism, basically. They take away the atmospheric commons from the others, pollute, built on that energy, their social foundation. I'm doing well. We're all pretty. We're doing great in the global north, right? Wrecking the planet, and the developing countries, they are, as we said before, don't have achieved these social thresholds and don't break biophysical boundaries yet. Of course, they could get there, and we have to help them not get there, by funding a lot. We're barely scraping together 100 billion per year, but this needs to be much more help, reparations, indeed. So this is Jason Hickel last year in the Lancet Planetary Health Journal. He just looks at the planetary boundary for climate change, which is 350 parts per million. We're now, I think, at 415 or so. So we broke that boundary in 88, and he just calculates, well, given that carbon budget 350, you can assess, if you assume every person, and I think it's a very fair assumption, should get the same amount of the global commons as a fair per capita distribution. You can ask, well, which countries are responsible for this overshoot that we already have? And you see here the United States, 40% responsible, the EU, 42% responsible, or Europe, the rest of the global north, and the global south, very little responsibility for this overshoot. So it's a kind of a travesty that we're talking about net zero by 2050 for the global north. We don't have a carbon budget, based on this equity and fairness considerations. And indeed, Anderson and others don't take that far, but also taking into account just what we agreed with Paris, our mitigation rates, our decarbonization rates need to accelerate much more. And, we need to reach net zero in the 2030s, not in 2050. This doesn't mean, of course, that developing countries like China and India don't have a role to play. There's a huge role to play, and they have been responsible for the acceleration of emissions in the last 30 years because they develop. But that means, in just of fairness, there's a vast disparity here. As I said earlier, it's really a form of climate colonialism. So we again taking the atmospheric commons from much of the world. And there's a great event which I really highly recommend, with Nimo Bassi and Nurata Mittal talking about these issues. And there is a case for climate reparations. There's a great recent article by David Wallace-Wells on that. So climate justice is really key here. And so, okay. So let's take a step back. So really, it's power clustered into different areas. The Davos cluster with the fossil industry, setting the narrative, and these international climate treaties. Mostly the global north, of course, have the power there with many more delegates. The global south, setting the agenda, setting the narrative, enabled consciously or unconsciously by a community of modelers, economists that make assumptions that are not value neutral, but that are perpetuating basically their worldview in some sense. And the ostrich cluster, where I belong to. I haven't looked into the climate crisis for the last 10 years, only looking at my individual consumption behavior, but clouded by the comfort of my own life and the distance of these climate impacts. And the majority of people are in basically because they don't feel the impact, and because they're doing well, and because they have the power, the top 1%, to set the agenda, have perpetuated the delay in action. And in this context, in the context of fossil fuel industry and power, Bill McKibben, I think in September, gave a talk, and he said, and I'm quoting, "I've been there all along, and it had taken me too long to figure out what was happening. I wrote the first book about climate change, and I kept writing more books and articles and having symposiums on the theory that if we kept piling up enough data and reason, eventually the powers that would get to work. Why wouldn't they? I thought we were in an argument, and it took me too long to figure out that we won the argument, but that didn't mean anything. We won the argument. The science was entirely robust and clear. We were just losing the fight. Because the fight wasn't about data and reason. The fight was about money and power, which is what fights are always about." I'm gonna have a short pause here. Maybe you stretch your leg, look how you're standing or sitting, getting a coffee or tea, drink some water. Okay. Fourth part. What can we do today? And here's Bill McKibben again, a hero of the environmental movement, saying, "It's easy to feel pessimistic about the climate. It's very easy to feel pessimistic. But we've got two big things on our side. The first thing is the enormous drop in the price of electricity from solar and wind and renewable energy sources. So here, the price of solar declined by 90% in the last 10 years. The price of onshore wind by 70%, batteries, similar decline, the storage of energy. Coal only, decreased 2%. Nuclear actually increased. So there's a dramatic reduce in the cost of energy from these renewable sources. And Carbon Tracker, who coined the term the carbon bubble, I think in the early 2010s, had two reports this year, the last year, and they said, look, how to waste over $500 billion. It's already cheaper to invest in renewable energy than coal in all major markets. Actually, for half the coal plants they're running today, you should stop them, build renewable energy sources, and use electricity and energy from there. You'll be better off. And I think this was this year, saying the sky is the limit. The solar and wind energy potential is 100 times as much as global energy demand. Yeah, and the land required for that is actually smaller than we're currently today using from fossil fuel infrastructure. So it's really an abundant, cheap energy source is down the line. And this wasn't the case just 10 years ago. Okay, so this is an enormous, enormous achievement. The second thing is this uproar of civil society, of climate movements. We have the Fridays for Futures, we have Extinction Rebellion, we have the Sunrise Movement in the United States, we have Rise Up in the Global South, really shifting the public's perception on the issue, and forcing policymakers and politicians to treat it as an emergency. They don't do it yet, yeah, but they've moved a lot from just 5 years ago. So if you talk with them, climate scientists and economists and people working in that area, some of them actually say, look, I've never been as optimistic as I am today because of these two reasons. And we have made progress. So this is from the New York Times before the Glasgow climate conference, COP, historical emissions. And before Paris, we were on a path of about 4 degrees of warming by the end of the century. But we'd continue to burn a lot of coal and fossil fuels and so on. That is not the case anymore. Yeah. So currently we're on a path for about 3 degrees. We shaved off 1 degree due to renewable energy and so on and so forth. It's still catastrophic because we may have, as I argued earlier, underestimated the climate impact significantly. So 3 degrees could be the new 4 degrees if you want. But we have made progress. There are pledges, of course, and people calculate new pledges and so on. Doesn't mean anything as long as it's not, implemented. But so there's still a long way to go to go to 1.5 degrees. But we have made progress, and there are these two big things on our side: renewable energy and civil society, climate movements. Now, what can we do? What can you do? What can I do? And Christian Nielsen et al. In Nature Energy, a month ago or so, talked about the different roles we play. We play the role of a consumer, of an investor, a role model, of an organizational participant, and of course the role as a citizen. So let's look at them in turn. In terms of the consumer, certainly we are in the global north, rich countries. Remember, look at the United Nations Mission SCAP report and see where you are. We have a lot of opportunity to reduce our carbon footprint. We can stop lower air travels, stop driving petrol cars, reduce meat consumption, especially beef, so switch to a plant-rich diet, and then talk about it, to shift social norms and bring contagion. There's two nice guides on the topic, also a research paper, Ivanova et al., quantifying the individual, basically, carbon emissions from consumption options. So there's a lot of improvement, I think, here for the global north and for us individually. We have to be a little bit careful to not blame the individual all the time. I mean, remember, the carbon footprint was born out of the marketing of British petroleum or beyond petroleum in the early 2000s. But there is a lot of room here for us and to talk about it and create systemic change. It has to come from the bottom. So this is the consumer side. In terms of an investor and organizational participant, I mean, you can divest your personal stocks from fossil fuel investments and in agriculture, industrial agriculture. You can organize to get organizations to divest. I mean, we had this in the pension fund in the Netherlands recently. You can donate to environmental organizations, but just set a recurrent donation to 2 or 3 and then forget about it. I mean, you won't notice it even if you're in that particular income bracket. I don't notice it, and I'm a PhD student. Give an influence through your position and your status. So if you are likely a high socioeconomic person, you may be a professor, you may run a business where you can put the climate emergency on the table. You can talk to people, you can organize lectures, workshops, you can think about high-level interventions. You can say, look, we don't really need all this meat in the cafeteria or at parties. We don't really need to fly every week or every month to some particular client because we need to do some business deal. So you can change your organization or the organization you're part in. But most importantly, probably, is as a citizen to vote and to talk about the climate crisis and to really organize, to mobilize, to get together with other people, organize, and to mobilize. So it doesn't have to be, blowing up pipelines. It doesn't have to be getting arrested on streets and blocking roads. Whatever you're comfortable with. I mean, if you're a parent and you've noticed in your kids' school that they serve a lot of meat or they're very energy efficient and so on, you could get together with other parents and then say, look, we think there's an issue here. So it really needs to be, we need to dedicate some time, if you want, to change the world. Yeah, it's not enough to say, oh, I'm swapping the steak with the vegan burger, which it absolutely you probably should. Also, is more healthy. But we need to dedicate some time to organize and to really push for change. Yeah. So I talked about tipping points in the climate system. There are also tipping points in the social system, with the climate movement, and that there are sensitive intervention points that we can think about individually and as a society, and to push us basically from a business as usual state into a decarbonized state. And historically, huge transformations have happened on a short timescale. So this is here from the United States mobilizing for World War II, and there are there are posters, saying when you ride alone, you ride with Hitler. Yeah, join a car sharing club, or the consumer's victory pledge. As a consumer in the total defense of democracy, I'll do my part to make my home, my community, my country ready, efficient, and strong. I'll buy carefully. I will waste nothing. I will conserve material. I will buy war bonds, to fund the war machine. Government spending rose tenfold. We had speed limits. The United States had speed limits. The manufacturing of cars, was banned. With a rationing of gasoline, income taxes shot up to 94%. Of course, this is in some sense a bad analogy because this was an immediate threat, the Nazis, and it was from the top down to fund the war machine. So there are difficulties with that comparison, but just to have a recalibration, because we've been hammered in that certain things are not possible and blah blah blah. If you mobilize from the bottom up and you really put things on the table again to say, look, we are in an emergency, we have to treat it as such, then things can happen rapidly. And we need these things to happen rapidly because we are in an emergency. We have 10 years, less than 10 years to decarbonize 50%. That is an enormous transformation and it requires a huge mobilization effort. So we need, as Peter Kalmus said, we need 1 billion climate activists to really shift the focus. We need to build broad-based coalitions. And so you need to be, if you listen to this, you need to be part of this. It's not enough to change individual consumption patterns, which is important and we should do, especially in the global north. But it's also important to mobilize and get together with other people and push the conversation forward in the action. There is, Christina Figueres says, the key architect of the Climate Paris Agreement, she says, we can despair and plunge into paralysis, or we can become stubborn optimists with a fierce conviction that no matter how difficult, we must and we can rise to the challenge. And there is really no choice. We have to become stubborn optimists. We owe it to our brothers and sisters in the global north. We owe it to our children and future generations, but we also owe it, to the next 10, 20 years to live, safely and in harmony and not in climate chaos and climate barbarism, to create a better world without air pollution, with cheap, abundant energy. But these are all positive transformations. Even though the climate will get worse, we can't decarbonize from today to tomorrow. There will be warming, also if air pollution goes away, but we can still create a better world in a warming world, and we have to mobilize for that. Okay. There's another pause here before I move on to show you En-ROADS and the climate simulator. Again, maybe stretch your neck a little bit or see how you sit. It's quite intense, at least for me. I'm not sure how you feel. So let me walk you through. I mean, I would do like an hour workshop to together try to limit warming to 1.5 or 2 degrees. But since I'm doing this alone now without an audience, I'm just going to give you an overview of this simulator, this tool. So this is En-ROADS, stands for Energy Rapid Overview and Decision Support. Was built by Climate Interactive and MIT, the Sustainability Initiative. And it's a kind of a simplified online simulator built with the best available science. So they're very up to date. They're updated frequently with the recent, for example, the IPCC report, which is climate science. They use the most up-to-date data from the World Bank and the International Energy Agency and the United Nations and so on. And they inform, they use that to inform the parameters or the model structure, and also to look at, well, how good do we hindcast past data, and they try to calibrate their models, to integrated assessment models to not be completely out in the universe. So they really do a great job, and you can look at, they have I think a 400-page documentation about how everything works, and you can also just change the assumptions. So if you don't like something here, you can say, well, actually, the equilibrium climate sensitivity, which is the amount of warming you get when you double concentration of CO2, is not 3 degrees, as the best estimate of the IPCC says, but maybe it's 4, maybe it's 2, or you can say, I don't know, it takes it takes fewer than 6 years to build a nuclear power plant, or you can say, actually, for every doubling of capacity in renewables, I get not a 20% reduction in price, but a 40% reduction. So you can do a lot here. But let's look at the tool. So on the left, you see the global sources of primary energy, and as we've mentioned earlier, in 2020, that's still mostly from coal, oil, and gas. And here you see basically a projection, a business as usual scenario from 2000 to 2100, which is the end date usually for these integrated assessment models. I mean, it's not that the world ends in 2100. Of course, if we don't reach net zero, it just continues to warm and get worse. But usually it's projected only until 2100. And on the right, you have greenhouse gas net emissions, so gigaton CO2 equivalent. So this is CO2 from land use and fossil energy, and methane and nitrous oxide F gases converted to this equivalent unit. And you find here you get a 6.3 degree warming by the end of the century. So this is current policies would lead to about 3 degrees. This is just a kind of business as usual or projection you could play around with and workshop some climate policies. And here you have the energy supply, so you can play with how much subsidies you want to give or tax coal, oil, and natural gas. You might know that the IMF, I think, recently estimated that they get up to 6 trillion subsidies in 2018, mostly because of air pollution was a huge burden on the healthcare system, and because of course the climate crisis. You can subsidize renewables or nuclear. You can have a breakthrough in a new zero carbon energy source. This would be nuclear fusion, which would then get added to the energy mix. You can have a carbon price, such as the energy supply. In the transport sector, you can electrify transport. You can electrify buildings and industry, and then increase the energy efficiency. Here, in terms of growth, you can change the population growth, and you can change economic growth. This is an aggregated climate simulator. So if you change here economic growth, it's over the whole world. So there's no distinction between the global south and the global north. And here you have land and industry emissions. You can stop deforestation if you want. You can reduce methane and nitrous oxide and F gases. And you also can have carbon removal technology. So afforestation, you can plant a lot of trees, or a technological carbon removal like bioenergy, carbon capture and storage, or direct air capture. So it's a pretty cool tool. One thing that is might be interesting for you is it's a nice way to view CO2 emissions from energy is through what's called the Kaya identity. So you have the global population here. So this is a projection for 2100. You have the GDP per capita. This is basically the economic activity, economic growth. And if you multiply that, you have the gross world product, right? You have all the monetary value of the economy. And then you can say, well, how energy intense is the GDP? How much exajoule do I need for $1 trillion of value created? And then you can ask, well, how carbon intense is this final energy, right? So something might be very energy intense, but if I use renewables, and that is very low carbon, or actually no carbon intensity compared to if I use fossil fuels. And then if you multiply that out, then you get the CO2 emissions from energy. And then you can see which levers you can change here to change these single factors. But okay, let's see what we can do here. So we could, for example, what's frequently discussed is a carbon price, very, very popular. So here we could say we want a carbon price of $50 per ton CO2, and we want to increase that from now up until 10 years to ramp it up. There's a recent review by Jessica Green in 2021 came out looking at the empirical evidence of how carbon pricing has reduced emissions, and she found there's actually very little actual emissions reduction for various reasons. And I encourage you to check that out. The current carbon price, the World Bank has a map of the current carbon price and emissions that are subject to a carbon price. I think it's 45 countries have one, and in total about 22% of emissions are subject to a carbon price. But it's on average, I think it's not even in the double digits. So 50% a ton, $50 a ton is for historical standards quite high. It's not high in terms of fixing the climate crisis, of course, but it is a start. So if I put in 50 here now, I wanted to look at how the energy mix changes, and to predict in your head how the temperature changes. So here I'm doing a 50 here, so 50 here, and it's quite a good reduction here. You can replay this. You shave off 0.5 degrees. And what you see in terms of the dynamics is that coal gets reduced quite harshly because it is the dirtiest fossil fuel. You have oil getting reduced maybe a little bit, but it substitutes for coal. Takes some of that increasing share. And then you have natural gas also decreasing a little bit, and then renewables increasing. So it's a pretty good intervention, and the question is, of course, how politically feasible it is. So if we go here from there are many other plots here, but what I want to show you here is the cost of energy here. We see that goes up because presumably the fossil industry will put that onto consumers. And then you have to be careful not to have that as a regressive policy. So if you don't support low-income workers who, for example, have to commute a lot and you have to use a lot of fuel to get to work, then they can protest and riot, and indeed that has happened with the Gilets jaunes in France. So you want to have that policy be progressive rather than regressive. And one you could make the carbon tax revenue neutral, so it just decrease other taxes. But I think what is nice, and Peter Kalmus has suggested this, is a kind of a universal climate income. So you just give the revenue back to the people, check every month, and that is progressive because mostly the rich use a lot of carbon emissions excessively, so they have to pay a lot into that pool, and then the low-income persons get proportionally more out of it. And that I think would make it acceptable to a wider public. Okay, so this is a carbon price. Let's go back to the primary energy. You can, of course, also say, like, look, carbon pricing has not done so much yet, and we know that the market might not be optimal or super efficient. So what we want is to make sure that we decrease coal, oil, and gas production. So that's what so let's look at coal. You can tax it more, but you could also have a kind of a intervention and say, I want to reduce the coal utilization over 10 years by, say, 75%. So it's quite a strong reduction. But if you do that, if governments could agree to do that, that would be a sure way to reduce these emissions rather than relying on market forces. And there was a report that came out, I think, a couple of weeks ago, the production gap report, that assessed how the production of these fossil fuels need to decrease by 2030, coal, oil, and gas, and how it's actually going. And coal needs to be reduced most dramatically. And I have, by the way, a lot of appendix slides that go into that mention the production gap report and so on and so forth. So, but let's do a 75% reduction here. And I want you again to see how the temperature changes. So we get another 0.2 degree. And I see that coal, the coal utilization gets reduced dramatically here. And there's of course an interaction. There's of course an interaction here, where if I hadn't done the carbon price, the reducing of coal would have done more, because now it's already reduced. So there's an interaction between policies. Now, I mean, so I mentioned air pollution is absolutely brutal problem, and you can also look at impacts here, air pollution from energy. Maybe let's look at the source. You see that, you know, coal is primarily responsible for all the air pollution, and if we of course reduce coal, we reduce the air pollution dramatically, and that of course sets free a lot of funds that you don't have to spend on healthcare. I mean, on average, across the world, air pollution slashes 2 years of life expectancy. There's brutal costs, respiratory illnesses, and so on and so forth. That money is then free to fund the transition, for example. And you could, I think, completely fund the transition with the healthcare costs here. But now we've only aggressively reduced fossil fuels. We can also say, we can also fund subsidize renewables more. So here we can look at the information, and there's a nice, you know, description of the dynamics and examples and equity considerations and co-benefits. And here we want to, for example, highly subsidize the renewable energy, and here make it 60% cheaper. And this is a 0.3 minus 0.3. Again, I want you to look at the temperature here. Didn't do much. Let's see. So what happened is that basically the renewables removed a little bit of the methane gas and natural gas, but we're still, you know, continuously burning fossil fuels. So what we could do now is reduce oil, again, slash that by 50%. Again, look at the slider. I'm winging this, so I'm just exploring the simulator with you. We do 50% reduction. It's quite a brutal transformation here. We shave off another 0.3 degrees, and we have to, of course, be a little mindful here. This is what happened at the workshop I gave for Correlate, that we're slashing a lot of energy, but we don't really have electrified transport or the buildings and industry yet. So they probably can't do much. You know, if you slash oil that much and you have a petrol car, then what are you going to do? I mean, you don't drive. So we need to electrify here transport and industry. So let's do that a little bit. We can again look at examples, key dynamics, and so on, and see what would be a good electrification target. And let's see, okay, we incentivize here, let's highly incentivize electrifications of the percentage of new transport. This is for road and rail. So we do here 50. You can again look at the temperature. Didn't do much, but at least now, you know, some of the people can drive with the car. You can also do air and water. Let's do maybe 30% here. Also won't do much in temperature, but it just allows us to actually use some of that energy from renewables. Similarly, we can do buildings and industry. Can look at key dynamics. New buildings, we do also here electrify heat pumps and so on. Get rid of the gas stoves. 50% here. Shaves off 0.1 in Fahrenheit. We can do energy efficiency tricks here that would reduce energy consumption overall, make it more efficient. But what is important is actually we have to get rid of the methane gas a little bit, and we have to think about other levers rather than only energy supply. So there are, of course, agricultural emissions that are a problem. So we could here reduce the methane and other gases. So methane in agriculture or in energy and industry. I'm just going to do a global reduction here of let's do 40%. you have to do the calculations of what is possible, and through what, through agriculture or so. But let's do a 30% here. It's just we minus 30%. We find that shaves about 0.2 degrees. Okay, and that is when you for example, you don't eat. This could be a demand side solution where you switch to a plant-rich diet, and you force the goddamn oil industry and the gas industry to actually fix their methane leakage from the transport and production of natural gas. I mean, that's a second largest source of methane emissions, completely, because it's so cheap. They just let it flare into the atmosphere. We can also here, let's phase out these well, actually, okay, let's do, we had minus 30 here, let's do minus 30 here and minus 30 here. We can also phase out these hydrofluorocarbons that we swapped. I think this was in, we fixed the ozone layer. There were F gases, and we swapped it with other F gases for refrigerants in industry, but that damage the atmosphere. So we phase out that by 2030, and that reduces also the CO2 equivalent. Doesn't shave off a lot of temperature here, but it's certainly something we should do. Let's see. Gas is still is still here, but let's increase the energy efficiency a little bit more. So transport, we do energy efficiency of new transport. So that we just do mandates and force the companies to innovate. That could be one thing. Another thing would just to have public transports, right? So build trains, bike lanes, and so on. So there's a lot of possibility for demand side solutions. Actually, a recent paper just came out yesterday by Felix Kotzig and others in Nature Climate Change, showing that demand side solutions can shave off 50% of greenhouse gas emissions by 2050. So changes in lifestyle, changes in how we travel and so on, how we eat. So it's going to be interesting when the IPCC report, Working Group 3 mitigation, comes out to see how that shifts the conversation. But let's do electrification here, a highly increased energy efficiency, 5%. We see that we reduce temperature, but we also reduce the amount of energy we're using. Let's do the same thing with buildings. And here we just retrofit. We do a lot of retrofitting. So let's see what the maximum is here. It's 20% per year. I mean, that's really a cheap. That's really a no-brainer in some sense. I mean, people in Britain now, insulate Britain, are arguing for this, right? You can actually save money by insulating your house and your buildings, because you don't spend as much on energy. So I think in Oxford, certain colleges got money for that, and they did it, and now they're saving money. So it's really an absolute no-brainer to do this. But there's still a lot of gas here, so let's reduce gas also by, let's see, 30%. Shave some energy out. And then we can, we should, I mean, there's this pledge now by 2030 to stop deforestation. So we can here stop deforestation. We do a reduction of 10% per year. That reduces, stops deforestation by about, I think, 2030. And that saves, I don't know, 3 gigatons per year CO2. So not brutal, but it does something certainly very good for the biodiversity and the indigenous population there. And you of course have to stop the Amazon turning into a carbon source. That would be absolutely dramatic. So we're already at 2.1. Some of the things I didn't do, for example, new zero carbon. So if you do a breakthrough here, for example, if you breakthrough in nuclear fusion in 2022, so next year, with the initial price that is equal to the price of coal, say we do this, okay, and imagine what happens to the degrees, is that nothing happens, okay? So it takes away from renewable energy, and because renewable energy is, carbon neutral, you don't get a shave off in degrees, so they just compete compete each other out. So that's not a real solution. You can increase the carbon price a little more. Let's see. We can do the energy efficiency here. This is for new buildings and infrastructure. When you build them, let's say with the improvements, we do improvements here. Also highly increase. So let's do 4% here. Was a brutal reduction in energy use because it's just more efficient. We still have some gas here. There's a great documentary actually in the 2010s on fracking in the United States called Gasland, where it's really kind of a marvelous documentary. The production very low budget, but the guy walks through the United States and its region and looks into communities where a gas well and fracking well has been built, and just the amount of pollution that sets free. So in some of them you see scenes where they use a water tap and they can burn the water because there's methane in it. So it's it's just a lot of air pollution, a lot of pollution, a lot of water use. I mean, they use a lot of chemicals, many of them actually unknown to the public in the fracking process. But okay, so we're at 2 degrees. I mean, we're at not well below 2 degrees, but we are at 2 degrees. We can, of course, do more interventions here. We can slow economic growth if you want. So if you switch in the global north, we say, look, we don't need this. We can say do the near term. We do this at, let's do 1.8, and we do here long-term growth of 1%. Shaves off a little bit because we've already done a lot. So if you look at the Kaya graphs here, you see that now the GDP per capita decreases, but at some point it doesn't help with the well-being in the global north. Energy intensity went down, carbon intensity went down. The energy supply is pretty much renewable now, and we are very energy efficient. Turn to default graphs. Now we can say, we said the carbon price here at 100. We really need more. I mean, some estimates up to 2000. So let's do 100 here and see how the dynamics change. Very little, and that's because coal is already pretty non-existent, as is gas and oil. So let's, for realistic purposes, let's do a 50 here and see whether we can bring it down through some more state intervention. So we have gas. Say we do this 50%. I mean, it's not a bridge fuel. Okay, it's a bridge to nowhere. Let's do 50% here. A little bit, not too much. We can. So we have to struggle a little bit here now. I mean, we population is not really a good. Let's say we have just 10 billion in 2100. Doesn't do anything. Let's say we have say we do the lowest population scenario that the United Nations forecast. So let's do here 9. Yeah, literally nothing. And that's also a common misconception. It's really the poor people who explode the population that's a problem. But as we've seen in the United Nations emissions gap report with the graph I've shown you, bottom 50%, they can actually increase the carbon emissions. It's really the rich people in the global north that are mostly responsible for climate chaos. So population is a distraction, as is nuclear energy. We need to build out renewable energies. We need to stop burning fossil fuels, fix agriculture, increase energy efficiency and electrification. For 1.9, now we can start to, I mean, we can do here, I mean, of course we can do more here. Let's do the 75% or so, shaves of 0.1 in Fahrenheit. Now we have to, work a little bit harder. So now we can get into the carbon removal business. Now, we could plant a lot of trees. So we can start with, say we have available land used for afforestation. If we look at the assumptions, you can ask, okay, how much land is actually there for for this afforestation here. Maximum available land is 700 million hectares. And then there are some other assumptions like how much is lost to fires, for example, and how long does it take to grow the forest. And here you can say, well, you use, let's say, 40% of that available land to build trees, and then you shave off 0.1 degree, but you also use a lot of land. So let's see what we find here in terms of land use. Land for growing biomass. So this is just planting trees. This is the size of India. So somewhere that land has to come, right? It may compete with food security, and it may also just not work. There's recent work by Fleischmann and others looking into historically how these afforestation projects have run and actually failed a lot of times. First of all, it's really another land grab, kind of in the global south. You take land away from people to build your stupid forests, and then you do monocultures that don't really work in the ecosystem, and so on and so forth. And I have some points on that in the appendix slides. So maybe let's be a little bit more, a little bit less eager here. Still shaves off a 0.1 degree, and then we can start with these, play with these technological carbon removal types, which are, nowhere near at the scale that we require them. There are bioenergy, carbon capture and storage. So remember, you grow biomass, you burn it for energy. Direct air capture, and you have other things like enhanced mineralization or agricultural soil carbon sequestration, where you say, look, actually, you take care of the land better so that it stores carbon. So this is maybe the least technological one. Let's see what the maximum potential from that guy is. So we have a carbon removal maximum. This is 5.5 gigatons per CO2 a year. So it's quite a lot that is possible. And let's say we can get to 50% here. Okay, we have 0.2 change 0.1 in Fahrenheit, and let's see, we also do direct air capture. We really fund this a lot, and because we have abundant and cheap energy, we can do it to 100%. Shaves off another 0.1 degree. Backside, I don't want to touch. So you see already what's getting sucked out here: agricultural soil carbon, direct air capture, afforestation, and we're at 1.7 degrees. So it's, I mean, it's kind of I mean, if you want, it's a little bit sobering to realize the extent of the system transformation that is required to get here in the simplified scenario to 1.7 degree. But it allows you also to give you kind of a reality check, like what are good interventions. Again, slowing population growth, nuclear, really not a key thing. The key is really to stop these fossil fuels from getting burned, keep them in the ground, and also fixing agriculture. I mean, we can do even more. Let's say we do a 80% reduction here, then we even get to 1.6. But it's of course difficult with the growing population who want meat and so on to fix our industrial agricultural system. It was maybe even harder than changing the energy supply, because in the energy supply we know, well, electrify everything, use renewable energy. But this is inroads, and we can, let's see whether we can actually have kind of a summary here. Yeah, so this basically tells you what we did, and tells you what we avoided, and the temperature outcome. And you can look at I mean, this is really a great tool. So you can look at different graphs again in terms of impacts. I've explored very little here with you. You can look at ocean acidification. You can decrease in crop yield, species loss. You can lose at sea level rise. Maps. This is quite cool, actually. So you can you have a whole map and see, okay, which regions, coastal regions get inundated. So here, this is Shanghai. There's a land that we saved by actions. This is a land that's at risk. This is the 21st century. But of course, again, the equilibrium may, once we've inundated all the things, you see, okay, wow, yeah, equilibrium, this already looks very bad, and we saved relatively little here in that part of Asia. Okay, so but other things, I mean, again, for air pollution, we saved like millions of lives here through reducing this. I mean, about 9 or 10 million people die every year. We saved them basically with abundant, cheap energy. With nicer cities. We have walking lanes. You know, you don't get to a city like Prague or Vienna and just have this brutal amount of cars that annoy you. But it's more like Amsterdam and Copenhagen and so on. Stop deforestation, fixed biodiversity loss, and so on. So yeah. So this is En-ROADS, and I'll stop it here. I just give you a quick yeah, so I will make these slides available to you. So I have about 140 or so, and there are a couple of them in the appendix. There's some books, documentaries, newsletters, podcasts I found very useful in the last year and a half. There's some more detailed figures on emissions, climate delay discourses, you know, these kind of things I've mentioned, not in detail. You can find them in the appendix with all the links to the literature and to interviews and podcasts and so on. And there's a nice, I wanna mention this here. There's a nice report that came out a couple of months ago on the system transformations required to limit 1.5 degrees. So we did some of that in En-ROADS, but they have a very detailed, they really go through the power sector, transport, and say, where do we need to be, where are we, how can we accelerate it, and so on. So this is really a key report if you're interested in the system transformations required. And I want to leave you with that picture here again, different roles you can play, I can play, we can play as citizens, consumers, investors, role models, organization participants, to bring about the change that is required, because it is going to be difficult. Yeah, it's an enormous challenge that we're facing as a civilization, as a species. But we can turn it around, and we can, in the process, create a better world. It's going to be tough, but it's, I think, also going to be exciting. You know, I mean, you want to be part of the transformation. It's exhilarating to join social movements and talk with people and say, like, okay, how can we bring about change? How can I use my, my skills that I've amassed over the last years, the creativity that I have, and really use it to make the world a better place. And so, yeah, I want to leave you with these words, and feel free if you have questions or want to get in touch with me to reach out. So thank you very much for your attention, and cheers.